At the start of the semester, we talked about the definition of chemistry as the study of matter and the changes that it undergoes. Well, those changes are accompanied by energy changes. And we mentioned energy a little bit early on in the semester, but let's talk about it in detail in this chapter. And so we need to lay out some definitions so that we'll know what we're talking about from different perspectives as we go through this chapter. And so the first definition we want to talk about is the system. And the system is the part of the universe that we're studying that's of specific interest to us. And the surroundings constitute the rest of the universe outside the system. So the system plus the surroundings equals the universe. So that's the first set of understandings that we need to have. The system is usually defined as the substances involved in chemical and physical changes. And so what we'll be looking at is what's taking place in the beaker or a flask or the calorimeter that we'll be talking about a little bit later in this chapter. So what we're looking at is a branch of chemistry that's known as thermochemistry. It's the study of heat. And heat, remember, is the transfer of thermal energy. So it's the study of heat, the transfer of thermal energy in chemical reactions as we go from reactants to products. Sometimes it will release heat, sometimes it will absorb heat. More on that later. So heat is the transfer of thermal energy. It's different than temperature. Temperature is a measure of the hotness or the coldness of something, whereas heat is showing that there's a transfer of thermal energy. And as I mentioned before, heat can either be absorbed or released during a chemical or physical change for that matter. And the SI unit for energy that we learned way back when is a joule, abbreviated capital J. We're very used to calories. And calories were defined as the amount of heat required to raise 1 gram of water by 1 degree Celsius. And a calorie is 4.184 joules. And now this is tricky and it's sort of conniving by the food industry. The calories that we're talking about are lowercase, small c calories, and not capital C calories, CAL, be that abbreviation. That's what a nutritional calorie is. And that's really a kilocalorie. And so when you're eating a 100-calorie snack bar, it's 100 big C calories. It's really 100,000 little c calories. And so to make it more palatable to you, they're calling kilocalories big C calories. It's all relative, so don't go freaking out that all of a sudden you're eating 100,000 calories. Relatively speaking, you're still just the 100 calories that you have been all along. But now you know what the truth in advertising is. So big C calories are really a kilocalorie, 1,000 calories. So let's see how different things measure up in terms of energy. So you set off a firecracker on 4th of July or New Year's Day, that's 30 joules. A stick of dynamite is 2 million joules. A ton of TNT, that explosion, is 4 billion joules. And so those are sort of explosive, very immediate and sudden releases of energy. If you're a combusted barrel of oil, that's about 6 billion joules. The kinetic energy of the International Space Station as it moves through space is 1.3 times 10 to the 13th joules. And a small nuclear bomb, 15 kilotons, is 6.3 times 10 to the 13th joules. And so the kinetic energy of the space station is moving quite fast. It's going around the Earth a little over an hour, so it's traveling 25,000 plus miles an hour. And when you do the kinetic energy expression, 1/2 mv squared, you're squaring that. Whereas a small nuclear bomb, then once again, that's a major explosion taking place very quickly, involving, once again, the Einstein's equation, E equals mc squared. So let's talk about energy changes for a moment. An exothermic process, exo, like exit, occurs when the heat is being transferred from the system to the surroundings. The system is what we're studying, and the energy, the heat is leaving. So that's an exothermic process. And so you can see in the little diagram, the heat's flowing from the system to the surroundings. And so the combustion of hydrogen plus oxygen to make water, it releases energy. So if it's releasing, it's giving it up, and so we can think of energy as being a product. And the picture that you see is of the Hindenburg exploding in New Jersey back in the early part of the 20th century. The opposite process is an endothermic process. It's when heat is transferred from the surroundings to the system. So an exothermic reaction, you saw the fire with the Hindenburg, that feels hot. An endothermic reaction is actually going to feel cool. Then it's going to absorb energy from the surroundings. And so mercury 2 oxide, as it decomposes, it requires energy to do that, and it actually will feel cold to the touch if you were to feel it. And so heat is flowing from the surroundings to the system in an